After we have find out the Fraunhofer diffraction of a single slit, let's try to calculate the Fraunhofer diffraction of a initial amplitude formed by n slits. Here is the initial amplitude, and we have many slits shown here. The total number of the slit is n, and in the center, the center slit is the number of n is 0, and this one with the n number is positive 1, and this one is the n number of positive 2, and in the positive direction the final number is n minus 1 over 2, and so you can find out the corresponding number in the slit located at the negative direction. And clearly, the initial amplitude for the center slit can be written as this one. The center slit have the corresponding number n is 0. So if the center slit can be expressed like this, then for the number n is 1, the corresponding amplitude can be written as u0 of x minus capital lambda, s0 minus capital lambda y0. Okay, here the capital lambda means the distance between two adjacent slits. So the distance between the center slit and the final slit in the positive direction will be this distance will for the center one to the final one here, the distance will be n capital N times capital lambda. Okay, and of course for the number of the n, the amplitude can be written as s0 minus n capital lambda y0. Maybe I should write down here the initial amplitude of slit of number n can be expressed as u sub 0 of s0 minus n capital lambda y0. Okay, so according to the number of the slit, you can find out its corresponding initial amplitude shown here. So how about the total initial amplitude? Clearly, the total initial amplitude can be considered as the summation of each slit. So we can say that the initial amplitude of capital N slits can be written as the summation of each slit. Okay, so as I have told you, if you can express the initial amplitude, then you can easily to find out the corresponding diffraction amplitude by performing the Fresnel integral. So to find out the diffraction amplitude of this problem of the n slit. You have to perform the convolution of the initial amplitude with the h function. Okay, so by the Fresnel integral, by performing the convolution of the initial amplitude of n slits and the h function, of course, you can obtain the diffraction amplitude of n slit. But how to find out this result? Let's go back to the Fraunhofer diffraction. Now, we only consider the diffraction amplitude in the far field region, so we consider the Fraunhofer diffraction. As the Fraunhofer diffraction, we know that the diffraction amplitude can be written as the following equation. Okay, by performing this integral, you can obtain the Fraunhofer diffraction, which is the diffraction in the far field region. But how? How to find out the result shown here? And we first perform some trick to simplify this equation. Let's consider that we can let x0 prime to be s0 minus n capital lambda, and we let y0 prime to be y0. So from these two definitions, we know that the ds0 prime will be dx0. And dy0 prime will be dy0. Okay, so let's consider this term. So let me correct here, no minus. Okay, consider this term exponential j k over z times s0x. This exponential function, if we use the definition here, it can be written as exponential j k over z. The s0 is replaced by s0 prime plus n capital lambda, and x here. Okay, so we just replace this one by this one according to the definition shown here. So we can say that this exponential function can be expressed as these two. Okay, but expand the term in here. So if this term can be written as this one, we can re-express the above equation to be the following form. Here, this term is also replaced by S0 prime. Okay? And for the following one, it will become this. Okay? By this definition, we just replaced the exponential function here by this, and then it can be rewritten as this one. And clearly, the above result can be considered into two parts. The first one is here, and the second one is here. And what will be the first one? The first one looks like that the Fraunhofer diffraction of the center slit. Okay, you have only one slit here, and this is the center one. So the first part here represents the Fraunhofer pattern of the center slit. What will be the second part? The second part just like a factor, right? So the result can be considered as the Fraunhofer pattern of the center slit times a factor, a function, which is function of theta and phi. Okay, we call this one as array factor. The array factor appears as we have more than one slit. If we just have one single slit, we will have this one, and we will have only one this. But if you have more than one slit, then you must multiply the result of single slit by this factor. So this factor is induced for the array, a slit array. So we call it array factor. Okay, but what is the physical meaning of the array factor, and how can we obtain the expression for the array factor? Let's see. According to the result, we know that the array factor is a function of theta and phi. Okay, and it is the summation of exponential j k over z times n capital lambda. And we know that in the coordinate, the z is r cosine theta, and the x is what? Is r sine. Oh, sorry, I forgot to write the x here. R sine theta cosine phi, and the y will be r sine theta sine phi. Okay, and if we consider the parallel approximation. As for parallel propagation, we know that the k vector will be very close to the z-axis. This means that the theta value will be very small. As theta is very small, cosine theta will be approximated to be 1. So this value z will be approximated to be r if we consider the parallel approximation. So we can say that under the parallel approximation, the z over x can be I shall write the x over z can be approximated to be sine theta times cosine phi. And we can take this result back into here. Clearly, you see we have x over z in the exponential term, right? So for a parallel approximation, the array factor can be written as, okay, by replace the x over z with this term. And of course, this is a geometry series. So we can easily obtain the result or the summation of this series. So the a function can be obtained as 1, I should write it like this, exponential minus jk Okay, the summation of the geometry series can be written as this one. And this one can be arranged as the following expression. And this will be the array factor we have defined here. Okay, so if you have more than one slit, the Fraunhofer diffraction pattern can be obtained by the Fraunhofer diffraction of the center slit times the array factor expressed in this way. And now we want to know that how we will have the array factor shown here. Clearly, you see that the array factor is the summation of this term, and what will be the physical meaning of this term? Let us consider two slits. For the center slit, the number is 0. For example, this slit, the number is n, and clearly the distance between these two slits will be n times capital lambda. And for plane wave passing through the initial plane, we will have the field start from the center slit, and we will also have the field start from the slit of number n. And for observer at here, it will receive the field both from the center slit and the number n slit. And we know that the optical path difference between these two fields will be this distance. Okay? And clearly, this distance is n times capital lambda times sine theta. So what will be the phase delay between these two fields? The phase delay between these two fields will be the k vector in the plane. The k vector in the xz plane can be written as k cosine phi times the optical path difference here, n capital lambda sine theta. So this one is the projection of k times the path difference. So this one is the phase delay of the field from the n slit to the field in the center slit. So for each slit, the field to the observer will have a phase delay compared to the center slit, and it can be written as this term. And you see, this term will be the same as this term, right? So this term here and this term here just represents the phase delay for the field from the slit compared to the center slit. So each slit have the phase delay compared to the center slit, and the summation of the delay of each slit will form the array factor shown here. That is the physical meaning of the array factor.